At 14:23 local time, a heavily modified Su-27 was maintaining a flight profile just 60 meters above a winding river valley, heading directly toward a strategically vital dam controlled by the regional alliance. Destroying this infrastructure was identified as the single critical variable required to paralyze the opponent's supply chains and reinforcements to the Eastern Front. While the mission had proceeded according to the flight plan, the tactical environment shifted in a heartbeat. The pilot's radar warning receiver emitted the harsh, continuous scream that signals a terminal threat. A missile was in the air. The pilot calculated a window of exactly 18 seconds before a high-velocity interceptor would detonate within the lethal radius of his airframe. He slammed the control stick to the right, pulling a sustained 7G turn into the narrowest corridor of the valley. Above him, at 8,000 meters, the interceptor was already descending along its ballistic arc. In 14 seconds, its active seeker would engage. In 16 seconds, it would be directly over his position. The pilot pushed into negative Gs, diving toward the churning river surface, utilizing every centimeter of terrain masking provided by the jagged cliffs. Water spray was kicked up into the engine intakes as the jet bottomed out at a terrifying 40 meters of altitude. The warning system detected a second launch, then a third. A local battery was firing a full salvo at the narrow exit of the valley, calculating the exact point where the jet was predicted to reappear. However, the defensive systems had made a critical algorithmic error. They were targeting the space where a standard Su-27 should be, not where this specific aircraft was. The incoming missiles utilized a two-stage guidance logic. For the initial 80% of their flight path, they relied on pure inertial navigation toward a predicted intercept point, receiving course corrections from ground-based radar every 0.5 seconds. But these corrections are only as reliable as the track quality. When the radar track quality falls below 60%, the updates become mere statistical guesses. Within Su-27 pulling 7Gs at 40 meters behind massive terrain features, the track quality plummeted to 15%. This is where the aircraft's thrust-to-weight ratio of 1.09 became the deciding factor. Unlike older generations of fighters, this jet could sustain these high-G maneuvers without bleeding its kinetic energy. The pilot rolled the aircraft inverted, pulling through a split S that dropped his altitude to 20 meters, then immediately reversed into a climbing barrel roll that peaked at 300 meters. Each maneuver forced the incoming missiles to recalculate their intercept geometry in real time. As the first missile seeker went active, the pilot had 3 seconds. He rolled 120 degrees to the right and pulled into a northern tributary valley. The missile's seeker cone swept through empty airspace. Finding no target, it defaulted to its impact, fusing logic, and detonated 400 meters behind the jet. The second and third missiles suffered an identical fate. Their seekers unable to distinguish the aircraft from the surrounding terrain. By the time the fourth missile reached the area, the Su-27 was 6 kilometers away and accelerating. A full launcher had been depleted for 0 confirmed hits. In the grand architecture of this conflict, the Krasny Bor Dam is not merely a concrete barrier. It is the beating heart of the regional alliance's industrial machine. For years, the stalemate in the Eastern Corridor has remained frozen, but the strategic simulation indicates a critical shift. This hydroelectric facility provides over 4,000 megawatts of reliable energy to the specialized automated complexes located in the deep rear. These are not civilian factories. They are high-capacity manufacturing hubs, producing the next generation of autonomous drone swarms and charging the massive capacitor banks for long-range energy weapons. To dismantle this node is to effectively sever the central nervous system of the opponent's logistical network. The strategic map reveals a stark reality. Without the power generated by these specific spillways, the automated assembly lines grind to a halt within 72 hours. The ripple effect extends across the entire theater of operations. High-output fuel pumps, regional radar arrays, and subterranean hangars all rely on this specific power grid. It is the primary gravity point for the current campaign. Yet, the cost of a conventional airstrike using a standard wing of bombers was deemed unacceptable by High Command due to the extreme saturation of high-tier air defense systems in the area. This tactical reality necessitated a high-risk, single-ship penetration mission using a pilot with exceptional low-altitude experience. The choice of the Su-27 airframe was a calculated irony. In a world dominated by fifth-generation stealth and quantum-linked sensors, this mechanical relic was selected for its rugged airframe and the absence of some of the complex electronic signatures that modern AI-driven interceptors are optimized to identify. For the pilot, known by the call sign Kozak, the mission represents more than a tactical objective. It is the intersection of legacy human skill and the cold efficiency of modern attrition. He carries the weight of a strategic defiance, acting as a living variable in an equation otherwise dominated by machines. The river valley below him is a corridor of history, leading toward a target that defines the boundary between victory and total logistical collapse. Every kilometer of flight represents 1,000 hours of strategic planning and the singular determination of a man flying against the current of technological time. To understand the impossibility of this mission, one must analyze the defensive architecture protecting the target. The regional alliance has transformed the airspace around the dam into what military analysts call a dead zone for traditional aviation. At the outer edge of this perimeter lies the S-500 Prometheus, a system designed to engage targets at the very edge of space. Its interceptors, the 77N6 series, travel at hypersonic speeds exceeding Mach 9. These are not just missiles. They are guided projectiles of pure kinetic energy, capable of shattering any aircraft upon impact. However, the S-500 is optimized for high-altitude threats, creating a theoretical vulnerability for a pilot brave enough to skim the jagged terrain of the valley floor. Yet, the true terror of this defensive network is not found in kinetic missiles, but in the invisible spectrum of the Krasuka 4M Quantum Electronic Warfare Suite. This system creates what is known as the quantum fog. Unlike traditional jammers that simply broadcast high-power noise to drown out signals, the Krasuka 4M utilizes quantum tunneling interference to subtly alter the timing data of satellite navigation systems. By transmitting carefully crafted false signals that mimic real GPS timestamps, the system confuses the internal clocks of incoming precision-guided munitions. Even a discrepancy of 1/1,000,000th of a second in timing can translate to a position error of 300 meters. For a weapon intended to strike a specific joint in a dam spillway, such an error renders the attack useless. The density of this electronic interference is unprecedented. At low altitudes, the system focuses its 4 antenna arrays directly on the river network, saturating the valley with 500 watts of concentrated jamming power. This creates a scenario where standard receivers show a total loss of signal strength dropping from a healthy -30 decibel milliwatts to a complete blackout at -142 decibel milliwatts. The regional alliance believes this shield is impenetrable, as it effectively blinds any weapon that relies on external data for its terminal guidance. But every electronic shield has a physical limit. The antennas are optimized for low-altitude coverage to prevent cruise missile strikes, creating a narrow, unintended null zone high above the valley. This flaw in the quantum geometry is the only reason the mission has a mathematical chance of success. It is a razor-thin gap in the enemy's vision, waiting for a pilot desperate enough to climb into the light. The aircraft at the center of this simulation is the Su-27 SKM, designated by tactical planners as the legacy flanker. While its silhouette is a remnant of 20th century aerospace engineering, its internal architecture has been stripped and rebuilt for the high-intensity environment of 2035. This specific airframe was selected not despite its age, but because of it. In an era where the regional alliance's sensors are tuned to detect the specific carbon fiber composites and frequency-selective surfaces of fifth-generation stealth fighters, the Su-27's predominantly titanium and aluminum construction presents a different, often disregarded, radar profile. Beneath the skin, the legacy flanker is powered by twin AL-31F engines, each capable of generating 27,500 pounds of thrust. This provides a thrust-to-weight ratio of 1.09, allowing the pilot to maintain high energy states during sustained 7G maneuvers at sea level, a feat that newer, more fragile airframes struggle to match in the dense air of the lower atmosphere. The aircraft's wing loading of 545 kilograms per square meter ensures stability during high-speed, low-altitude terrain masking, where the margin for error is measured in millimeters. The most significant upgrade is the L-150 Pastel radar warning receiver. This is no longer a simple detection device. It is a passive signal intelligence suite. By analyzing the pulse repetition frequency, scan patterns, and signal strength of enemy emitters, the system can triangulate the location of ground-based batteries within a 200-meter radius, without the pilot ever activating his own radar. This allows for a dark approach, where the aircraft remains electronically silent until the moment of engagement. Mounted on the centerline pylon is the mission's primary payload, the HGV-X Meteor. This is a hypersonic glide vehicle designed for pure kinetic destruction. It lacks an explosive warhead, relying instead on an 800-kilogram solid tungsten penetrator and the physics of extreme velocity. To deploy this weapon, the Su-27 must act as a first-stage booster, carrying the Meteor to a specific release window. It is a fusion of old-world mechanical durability and next-generation kinetic lethality, a legacy fighter reborn as a delivery platform for a weapon that moves too fast for even the most advanced AI to intercept. The Su-27 crossed a 2-kilometer gap between ridgelines, exposing its titanium skin to the searching beams of a mobile fire control radar, positioned 3 kilometers to the south. In less than a second, the track quality jumped to 75%, a high confidence threshold for a successful engagement. The battery operators, trained for precision, launched 2 interceptor missiles in rapid succession. These projectiles utilized a sophisticated 2-stage guidance system. For the first 80% of their flight, they moved on pure inertial navigation toward a point in space predicted by the ground-based radar. However, the ground operators had underestimated the kinetic resilience of the legacy flanker. The pilot, sensing the lock through his L-150 Pastel receiver, executed a maneuver that pushed the aircraft to the very edge of its structural integrity. He rolled the jet inverted and pulled through a split S, a high-risk dive that dropped his altitude from 60 meters to a mere 20 meters above the river's surface. This sudden change in elevation and direction caused the ground radar's track quality to plummet from 75% to a dismal 15%. In the world of high-speed interception, 15% is little more than a guess. As the first missile's active seeker went live, it was met with a wall of terrain returns. The Su-27 had effectively disappeared behind a massive granite ridgeline at the critical moment of seeker activation. The missile's logic computer, faced with a sudden loss of target data, attempted to recalculate the intercept geometry based on the last known velocity. But the pilot had already reversed his turn into a climbing barrel roll, peaked at 300 meters and dove back into a perpendicular canyon. The first missile, unable to find a target within its 60-degree seeker cone, defaulted to its impact fusing and detonated 400 meters behind the aircraft. The second missile, following the same corrupted data, suffered an identical failure, exploding harmlessly against the canyon floor. The explosion sent 4,000 tungsten fragments into the air, but the flanker was already 6 kilometers away, shielded by the Earth itself. The defensive battery had emptied its ready-to-fire racks for zero result, proving that even the most advanced predictive algorithms are no match for a pilot who understands the geometry of the terrain better than the machine trying to kill him. As the Su-27 approached the final 20 kilometers of its run, the tactical situation reached its most critical juncture. The HGV-X Meteor mounted beneath the wing was ready for deployment, but its internal guidance computer was struggling to maintain a lock. The signal strength for its GPS coordinates from the orbital satellites dropped from a healthy negative 30 decibel milliwatts to a catastrophic negative 142 decibel milliwatts. The quantum electronic warfare system protecting the dam was flooding the valley with corrupted timing data, making it impossible for the weapon to calculate its position with the required 3-meter accuracy for a kinetic strike. The pilot, Kozak, knew there was only one solution, and it was a maneuver that felt like a suicide mission. Based on high-level intelligence briefings, the enemy's jamming antennas were optimized for low-altitude saturation, creating a narrow, vertical gap in the coverage at precisely 3,500 meters. To hit the target, the pilot would have to trade his only defense stealth and terrain masking for a few seconds of clean satellite data. It was a gamble that would place him directly in the crosshairs of every active sensor in the region. He pushed the twin throttles to full military power, engaging the afterburners. The AL-31F engines roared to life, producing 55,000 pounds of combined thrust. He pulled the control stick back sharply, and the aircraft rocketed upward at a 70-degree nose-high angle. The rate of climb peaked at 45,000 feet per minute. In less than 15 seconds, the jet shot from 60 meters to over 3,000 meters, emerging from the shadows of the canyon into the blinding sunlight of the upper atmosphere. The sudden appearance of the flanker on every radar screen within a 100-kilometer radius triggered an immediate and violent response. Multiple surface-to-air missile sites and an orbiting A-50 command aircraft registered the target. Warning lights in the cockpit flashed red as fire control radars locked onto his position from multiple vectors. At 3,400 meters, the GPS receiver on the Meteor finally blinked from red to green, acquiring 8 authenticated satellites. The pilot had exactly 10 seconds before the first hypersonic interceptor would reach his altitude. His hands moved with practiced precision, entering the final authorization code into the tactical display to synchronize the weapon's inertial navigation system with the authenticated satellite data. The weapon's status changed from not ready to ready. With a single press of the release button, the Meteor fell away from the pylon. Without waiting to see the results, the pilot immediately rolled the aircraft into a vertical dive, pulling 9 Gs as he headed back toward the relative safety of the valley floor, while a barrage of missiles closed in on his last known coordinates. The moment the HGV-X Meteor cleared the centerline pylon, a mechanical sequence began that would determine the success of the entire operation. As the weapon fell away from the Su-27, spring-loaded actuators fired simultaneously, driving 2 pairs of wing panels outward from their recessed channels. Each panel rotated 90 degrees into a locked, rigid position in less than 0.3 of a second. The tail fins deployed in a similar fashion, providing the guidance computer with the necessary control authority. Within half a second of release, the Meteor had transformed from a blunt cylinder into a 6-foot wingspan hypersonic glider. As the weapon descended, the high-intensity jamming from the ground once again blinded its GPS receiver. However, the brief 10-second window of clean data at 3,500 meters had been sufficient to update the internal inertial navigation system to a near-perfect state. Inside the guidance computer, a ring laser gyroscope, accurate to 0.003 degrees per hour, and accelerometers capable of measuring changes as small as 10 micros-Gs took over. These sensors were now the only thing guiding the weapon toward its target. The guidance algorithm calculated the optimal trajectory for maximum kinetic impact. The weapon was not designed to explode. It was designed to penetrate. According to the laws of physics, kinetic energy is equal to 1/2 of the mass times the velocity squared. By accelerating to Mach 5 in its terminal phase, the 800-kilogram tungsten penetrator would deliver an impact force equivalent to several tons of high explosives, but concentrated on an area no larger than a dinner plate. The meteor entered its terminal dive at an altitude of 500 meters. Its control surfaces commanded a maximum nose-down pitch, driving the impact angle to 73 degrees. Its velocity increased from 280 to over 400 kilometers per hour in a matter of seconds. The radar altimeter counted down: 100 meters, 50 meters, 20, and then impact. The tungsten rod struck the specific construction joint where the spillway met the main dam structure. The impact created a pressure wave of 4.2 million psi at the point of contact. Concrete designed to withstand 5,000 psi of compression shattered instantly, turning into a fine powder. The sheer velocity of the rod carved a crater 8 meters wide and 4 meters deep, sending cracks radiating outward along the dam's structural joints. The structural integrity of the dam was compromised in a heartbeat. Water pressure, exerted at a force of 14,000 tons per square meter, found the new weaknesses and began to push. Within 30 seconds, a 15-meter section of the spillway face collapsed entirely under the weight of the reservoir. A wall of water thundered through the breach at a rate of 12,000 cubic meters per second. The energy grid of the regional alliance vanished from the monitors as the turbines were submerged and destroyed. The kinetic hammer had fallen, and the strategic landscape of the Eastern Front was permanently altered. The collapse of the Krasny Bor Dam sent shockwaves far beyond the flooded river valley, triggering a cascade of logistical and strategic failures within the regional alliance. Within 60 minutes of the breach, the automated industrial complexes in the deep rear experienced a total power blackout. The assembly lines for autonomous drone swarms, which relied on the consistent 4,000 megawatt output of the dam, ground to a halt. In the following 72 hours, the absence of these reinforcements led to a measurable degradation of the opponent's frontline capabilities. The strategic simulation indicates that this single mission achieved what months of conventional artillery barrages could not: the complete paralysis of the Eastern Corridor's industrial heart. On a global scale, the success of Operation Black Gorge has forced a radical re-evaluation of modern military doctrine. For years, the prevailing belief was that fifth-generation stealth and quantum-linked defense systems had rendered older, non-stealth aircraft obsolete. This mission proved otherwise. It demonstrated that a legacy airframe, when piloted with extreme precision and equipped with specialized kinetic weapons, can exploit the physical and algorithmic blind spots of even the most advanced AI-driven defenses. The quantum fog that was supposed to make the dam invulnerable was defeated not by superior technology, but by a pilot who understood the fundamental physics of the terrain and the limitations of electronic sensors. The cold calculation of the AI simulation core V3.0 reveals a stark cost-to-effect ratio. The total cost of the modified Su-27 and the HGV-X Meteor was less than 1% of the value of the infrastructure it destroyed and the defensive batteries it depleted. However, the data also highlights a variable that cannot be fully quantified: the human element. The pilot's decision to climb into the kill zone to acquire a GPS lock was a move that no purely autonomous system would have executed, as the probability of survival was calculated at less than 12%. It was this willingness to accept an irrational risk that allowed the mission to bypass the predictive logic of the S-500 system. The verdict of this simulation is clear. The future of warfare will not be a simple transition from human to machine, but a complex and unpredictable synergy between legacy durability and futuristic lethality. Asymmetry remains the ultimate weapon. While the machines of 2035 can process billions of data points per second, they still struggle to account for the intuition, desperation, and raw courage of a human pilot flying on the edge of the envelope. The mission was a success, but it serves as a chilling reminder that in the era of high-tech attrition, the most dangerous component in any weapon system remains the person behind the controls. This video content is a hypothetical simulation generated by artificial intelligence. The scenarios, tactics, and outcomes presented are based on theoretical models and public military data for educational and entertainment purposes. It does not reflect any real-world events, nor is it intended to be 100% accurate or a definitive prediction of future conflict. Viewers are advised that this is a conceptual what-if analysis produced by AI and should be understood as a work of strategic fiction. The immediate aftermath of the Krasny Bor incident triggered a seismic shift in global military intelligence. Within hours of the dam's collapse, satellite imagery confirmed a massive redeployment of strategic assets across multiple theaters. The regional alliance, realizing the inherent vulnerability of their energy-dependent infrastructure, initiated an emergency shutdown of similar hydroelectric and nuclear nodes, fearing a coordinated wave of kinetic strikes. This led to a temporary but severe energy crisis, causing global markets to fluctuate as industrial output forecasts for the quarter were slashed. For the first time in the digital age, the perceived invincibility of a high-tech perimeter was shattered by a low-tech entry point. Military observers noted a sudden surge in the valuation of legacy airframes on the international defense market. The flanker renaissance, as analysts termed it, saw nations scrambling to pull decommissioned fourth-generation fighters out of storage. The lesson was clear. Over-reliance on a unified, AI-driven sensor mesh creates a single point of failure. If the network can be spoofed, blinded, or bypassed by a pilot utilizing physical terrain, the entire multi-billion-dollar defense architecture collapses. Defense contractors began shifting R&D budgets away from pure stealth and toward hybrid resilience, combining modern electronic warfare with rugged, analog backup systems that do not rely on a centralized data link to function. Furthermore, the engagement between the Su-27 and the S-500 has redefined the parameters of beyond visual range combat. Military academies are now revising their curricula to emphasize manual terrain masking and high-G maneuvering, skills that were once thought obsolete in the era of long-range missiles. The simulation shows that several global powers have already begun testing dark flight protocols, where aircraft operate in total electronic silence, relying on inertial navigation and pre-programmed mission profiles to strike deep behind enemy lines. The psychological impact on high command structures was profound. The realization that a single, determined pilot could neutralize a strategic gravity point has introduced a new level of paranoia into defensive planning, leading to an arms race focused not on better sensors, but on more resilient, decentralized infrastructure. The simulation of the Krasny Bor strike marks a definitive turning point in the conceptualization of 21st century conflict. As the strategic horizon moves toward 2035, it is increasingly clear that the world is entering the era of hybrid warfare, a period defined by the violent collision of hyper-advanced technology and raw tactical ingenuity. The battlefield is no longer a transparent grid, where every movement is predicted and countered by a centralized intelligence. Instead, it has evolved into a chaotic environment of shadows and decoys, where the oldest rules of combat speed, surprise, and the absolute mastery of terrain still hold dominion over the digital domain. This mission was never solely about a single target or a specific airframe. It was a rigorous test of the fundamental assumption that machines would eventually render human instinct obsolete. The data generated by this simulation proves that while artificial intelligence can manage immense technical complexity, it cannot yet replicate the audacity of a pilot who intentionally chooses a path with a 12% survival rate to ensure a strategic victory. The future of global security will likely depend on this precarious balance, the cold, calculated precision of the machine, guided by the unpredictable spirit of the individual. As regional powers continue to develop increasingly complex defensive layers, the most effective countermeasures will not always be found in more advanced code, but in the creative application of physical force where it is least expected. As the simulated floodwaters of the Krasny Bor recede and the strategic dust settles, the lesson for future planners remains absolute. Technology is a force multiplier, but it is not a substitute for strategic wisdom. The next decade will be defined by those who can master the interface between silicon and the soul. This is the new reality of the front line, a place where the legacy of the past and the technology of the future merge to rewrite the rules of war. This video content is a hypothetical simulation generated by artificial intelligence. The scenarios, tactics, and outcomes presented are based on theoretical models and public military data for educational and entertainment purposes. It does not reflect any real-world events, nor is it intended to be 100% accurate or a definitive prediction of future conflict. Viewers are advised that this is a conceptual what-if analysis produced by AI and should be understood as a work of strategic fiction.